I'm Thiago Alves, and I'm gonna be talking about our work, which is called Towards Adversarial Attack Resistant Deep Neural Networks. So, what are adversarial examples? Uh, in the case of this work, we're focusing on image classifiers. So, an adversarial example is when you get an original image and you inject some controlled noise to that image in such a way that it, to the human eye, it still looks like uh, it's the same image, or it would be classified as the same class, but to the target uh, classifier, it gets misclassified as something else. So here we have an example of in the upper left we have the image of a bird that originally it gets classified by a deep neural network that does image classification in the Cipher 10 dataset. Originally it gets classified as bird with 99.9% of confidence, and then after we apply an attack to devise an adversarial example, to the human eye, this image still pretty much looks like a bird. Of course, it looks like a bird. It has some differences, some noticeable differences, but when you run it through the same image classifier, it gets classified as a cat with 94% confidence. So in the bottom row we have the same thing done to a frog that after the attack gets classified as a ship. So there are traditionally there are two approaches to devising this adversarial examples. The first one will be a white box attack or white box approach, which is when you have complete knowledge about the machine learning model you want to attack. So this allows you to perform the method, which is gradient ascent or descent, either way, very fast, because you can analytically, since you have complete knowledge about the model, you can have knowledge about the architecture of the neural network. You have a knowledge about the weights, so you can analytically calculate the gradient. So it's very fast, and then you can perform gradient ascent very fast. But in the cases where you only have input-output access to the model, you know nothing about the model at all. You just can input your image and receive the classification with the confidence level. You need to use some kind of finite difference method. You need to do a numerical differentiation to approximate the gradient, to perform the gradient descent, and obviously this is much less efficient. So we have so in this work we focus on the black box attack, preventing black box attack, right? So here we have an example of a run of a black box attack. We picked for this example, a grayscale image of a deer, because to perform this attack in grayscale images, it's much faster than with RGB. So just for the sake of simplicity, we picked a grayscale image. So in 3 iterations of the black box attack, I can get the regional image, which is an image of a deer, to get classified as a truck, applying this black box attack, which is gradient descent, using approximation with a numerical approximation of the gradient, and doing it iteratively. So we propose 2 defenses in this work. The first one is noise injection, and this defense relies on the injection of long-tail distributed errors to the output effects of the model, which is the confidence level of the model. You add some entropy, some with long tail distribution of this noise to the output, to the confidence level, so that a black box attack cannot converge whilst maintaining the functionality of the machine learning system for legitimate users, right? Since the error is most likely very small, it's gonna maintain the accuracy, the whole functionality for legitimate users. And we have the model pooling approach, which uses the inherent entropy of the training process, which is due to shuffling of the dataset and random transforms for applied to the input images of the dataset. So you basically train the same model multiple times, and you have a pool of this same model, but different instances, which you have some difference between them because of this inherent entropy. So this entropy impedes the conversion of the black box attack, because black box attack is depends on the numerical method, and with the entropy it cannot converge. So here we have two examples of runs of the black box attack when the two defenses are applied. And you can see that first we have on the y-axis we have the confidence level, and in the x-axis we have the number of iterations of the black box attack. So we can see that when we apply our defenses, the confidence level goes up and down, so it has a wave-like behavior. And this wave-like behavior basically suggests that the numerical method applied by the black box attack will not converge. So, to conclude, we propose two defenses against black box attack, and our experiments with the image classifiers using the Cypher10 dataset prove that both defenses successfully prevent convergence of the black box attack. Thank you.